So this session is related to doubts related to topic material, the assignment material. The first one is question number 4. A spring is there which is extended by 9 centimeter when a force of 6 Newton is applied. The limit of proportionality is not exceeded. Another identical spring is there joined end to end with a spring and the force of 4 Newton is applied. What will be the extension of the pair? Look, example, if there's a spring and when we apply a 6 Newton load, how much it increases in length? Like originally the unstretched length of a spring without any load, that's unstretched. Then we add a load, it changes by 9 centimeter. So this is a total extension or total increase in the length. In the question, they're saying now we connect the identical spring, the same springs end to end. So for example, this is spring 1, and then we connected another spring 2, and then we applied a 4 Newton load. So when we apply a 4 Newton load, this 4 Newton load is experienced, each spring will experience a 4 Newton load. So there will be a force of 4 Newton on spring 1 and there will be a force of 4 Newton on spring 2 because they are connected end to end. If they are connected side by side, it means the 4 Newton will be divided between them. Like if the spring system was like this and a 4 Newton is attached, so that time 2 Newton on each. But because they're connected end to end here, that's why each will experience 4 Newton. So we'll find the extension for spring 1 and that will be same for extension for spring 2, and the total extension will be the sum of the two extensions. So we have the ratio that if there is a force of 6 Newton, it is producing a 9 centimeter extension. So if there is a force of 4 Newton, how much extension it produces? X. We cross multiply, so how much extension? It will be 4 multiplied by 9, and that is divided by 6. So 4 multiplied by 9, 36, and 36 divided by 6, so it will be equal to 6 centimeter. So each spring, like there will be increase in length of 6 centimeter for spring 1 and there will be increase in length of 6 centimeter for spring 2. So what will be the total extension? The total extension will be 12 centimeter. That's why C is the right answer. Is it clear? Discussion? Next is question number 6 is there. Question 5 and 6 are basically related to the graph. So the Young's modulus refers to a slope. The greatest strength means the one which need the maximum force to break. So A is having the highest strength because we need a greater amount of force to break A. The Young modulus refers to initial slope. The one like to produce a small extension, we need a greater amount of force. So that shows it will have the highest Young modulus. So when we check the initial slope for each, like example for D, this is the slope, B, A, and when we check for B, B is much steeper than anyone. So it means for B we need a greater amount of force to produce a small change in length. And when we are checking the Young's modulus or the stiffness or the value of the K, we just check the initial slope. We don't see what happened afterwards. We just check the initial slope where the line is straight. So the one which is having much steeper slope, it means that is having the highest value of Young's modulus or stiffness or K. So in this case, B will be the right answer. Then question number 8. So a wood sample is clamped securely to a support, the light platform suspended from the wood. The dimension of the wood sample at X are known. The mass of 2 kg is added during a platform for the testing. The wood sample break at point X when the total suspended mass is 84 and the cross-sectional area of X at X is 1.3 into 10 power minus 5 meters square. Ultimate tensile strength. So we need ultimate tensile strength means maximum pressure needed to break this, that is 6 exponent 7. So ultimate tensile strength or stress is equals to force divided by area. And what about the force? Force is the load which we attach because the total mass suspended is 84. So it will be 84 multiplied by 9.8 because mass is not the force, weight is a force. So we convert the mass into weight by multiplying with gravity divided by cross-sectional area, that is given 1.3 into 10 power minus 5. So when we divide 84 into 9.8 divided by 1.3 into 10 power minus 5, so it will give us 6 into 10 power 7 Pascal or Newton per meter square, you can also say. Then part B, explain why this method of testing may produce a large value of true ultimate tensile strength. As you can read in the question, every time when they are adding a load, the mass of 2 kg are added to platform during the testing. Means what we did, like example, if this is the sample which we want to break, which is attached with a platform. So every time the total mass is 84 kg, but every time we add 2 kg, like 2 kg, then 4, then 6, 8, 10, until we reach 84 and it breaks. But that is not the right way because maybe, like example, we think it break at 84, but maybe it might break at 82.1, 82.2 because we are not adding 83 every time. We are adding 2 kg, like the difference between the mass which we add every time is 2 kg. So first we add 80, like till 80, then after that when we add 2 kg it will be 82, and then after that it will be 84. So when we add 84, we find that this break, the sample break, so we get the force using a mass, we got the weight, and using a weight, we got the force. But maybe the mass of 84 was not the responsible for breaking. Maybe the sample might break at 82.1, or sample might even break at 83. But we don't have these values as we are taking a greater difference in the masses every time, like 2 kg difference is there between the each set of result. That's why this is likely to produce higher ultimate tensile strength. Like the value of the force which we are applying, we think it is at 84 it break, but maybe it does not break at 84. That's why, so explain why this method of testing may produce a large value of ultimate tensile strength. So every time the mass which is added is 2 kg, so we don't have any result. Maybe it might break within 2 kg addition. So that's why it won't be accurate. Explain why the wood sample is used to test. Explain why the wood sample used for this test has this shape. So what is the reason why this shape we use? So that it can break at certain point. Like this will be the breaking point. Otherwise, what happen if it was having any like cylindrical object is there or rectangular object is there, so it can break from any point. We will not be sure which point it will break when we add a load. But using this technique, because it is narrow here, so when it is narrow, we have the formula that is stress is equals to force divided by area. So when area is small, it will be a maximum stress. So we can work out what will be the maximum stress applied on this object, as well as it will break at certain point only, like this point where it is narrow. Otherwise, if the whole sample was there and it's having, like, it can break from any point, so we'll not be sure of it. So why it's of 2 mark? 1 mark is for mentioning that it will likely break at a narrow point, and the second one, because it's having a small area, so that will give us the large ultimate tensile strength, or the maximum ultimate tensile strength. So it will break at a certain point and the maximum stress will be there in the center. The sample of a word of same type are not entirely uniform. What should be done to ensure reliable results when carrying out this? So because whenever we are taking a sample of the wood, the wood is not having a uniform density, like some region the particles are closer, some region the particles are away. So it's not like a uniform throughout. So what we should do to ensure that this is a true value, so we should repeat the experiment with different sample of the wood so that we'll get the true value. So this was question number 8. Then after question 8, question 18. The graph shows a stress and strain curve for two types of human bone under compression. So the bones are under compression, and this is the graph which we obtain for the two types of the bone which are under compression. One is cortical bone and another one is trabecular bone. Use the graph to identify and describe one property of cortical bone. So what we can identify one property using a graph, we can identify the stress. Like, it is having a high tensile strength because this is a breaking point. So maximum where stress is there, it can obtain or occur maximum stress applied on it before it break. And it is steeper, much steeper as compared to trabecular bone. So it shows that it is also having a high Young's modulus. So two things which we can identify: it will have a high or a greater or a large Young modulus, and the second thing we can also say, it will have a greater strength or high tensile strength. So greater Young's modulus, because the Young's modulus refers to a slope, like, of stress and strain graph. So as you can see, it is much steeper as compared to trabecular bone. That's why it will have a greater Young's modulus. And the second thing, it will have high tensile strength or compressive strength, because we are in the question they mentioned we are applying a force to compress it, so that's why it is having a high compressive strength. Like, maximum force, a greater amount of force is needed to produce a small compression. The second part, the table gives the information about two types of the bone. State difference between the compressive stress and tensile. Compressive stress means when we apply force to reduce the size, we call that as a compressive stress. But when we apply a force to increase the size, we call that as tensile stress. So the definition, you have to write a proper definition. So compressive stress, the force applied to reduce the size, or in this case, the force applied to reduce the bone or shorten the bone, we call that as a compressive, and tensile is refers to the force with that applied to increase the size or stretch the bone. State how the graph would be used to confirm the value of the Young's modulus for cortical bone. So what we can do, we can find the gradient, and that gradient will be the Young's modulus. Young's modulus means how much stress is needed to produce a small strain, or ratio of stress and strain is refers to Young's modulus. So you will mention, find the gradient, and gradient will give us the Young's modulus. Then a person of mass 90 kilogram stand on 1 foot. Shows that the maximum weight can be supported is about 70 times this person weight. Assume that all the weight is supported by femur, the thigh bone, and that is made of cortical bone. The cross-sectional area is given, which is 3.7 into 10 power minus 4. So first what we have to do, we have to use a table, because for a cortical bone, the maximum one is the tensile stress, another one is a compressive stress. So which one, and the Young's modulus is also given. So we have the formula, stress is equals to force divided by area. So first we will find how much force is needed. So which stress we should take, because this will be a compressive, like a person is not, when we are standing straight, it means our weight is trying to compress the bone. The thigh bones are being compressed when we are standing. So it means which stress we have to take, we have to take a compressive stress, and that is given in 170 megapascal. So we will write that stress is equals to force divided by area. The stress, that is 170 megapascal, means 170 to 10 power 6. Force we don't know, and area they give, that is 3.7 into 10 power minus 4. So this is minus 4, other side it will be multiplied. So we'll first get how much force, or the maximum force which it can bear or applied on it. So it is 62,900 Newton. That's a force. Now what is the weight of the person? Weight of the person, W is equals to mg. So weight is equals to mass multiplied by gravity. Mass of the person is 90 and the gravity is 9.8. When we multiply them, it will be 833 Newton. Now when we take a ratio, because that is they're saying, when this the maximum weight which can be suspended or supported is about 70 times the person weight. So person weight is 833 Newton, and the maximum force which can be applied is 62,900. So when we take a simplest ratio between them, so 62,900 divided by 833, the simplest ratio between them is about 71. So that is about 71. So it means like this value 62,900 is about 71 times 833. So it confirmed that it can maximum it can bear about 71 times the original weight. Then it is stated in a textbook that femur can support 30 times a person weight. Explain how the structure shown on the diagram could account for a difference in the calculated value. Look, in the calculated value, we got according to calculated value, it should support 71 times the weight, but practically it is only supporting 30 times the weight of the person. So what is the reason for that? As you can see, the structure, the area is not constant, area is changing. Here it's a small area, so it can bear maximum, as we have the formula, stress is equals to force divided by area. So if stress, the compressive stress, like force on it is, the compressive stress force on unit area is constant, so it means we can write stress into area is equals to force. And when we replace proportionality, the constant, it will come out to be proportionality. So it means area and force are directly proportional if we want to keep the stress constant. So here you can see there is a smaller stress, a smaller area, but in this part, so area is not constant for the bone. Area is changing. This region it's having a large area, below it is having a small area. That's why what happened as a result, because an average area won't be able to support, if it was having a constant, like bone is having a constant area, then there will be a constant maximum force which it can bear. But as you can see, the effective area, the area which we use in the previous part, we assume that its area to be constant. The cross-sectional area of the femur, we assume that is 3.7 into 10 to the power minus 4. But in reality, it's not same. It's different. Like it is changing continuously. This point we have different area. At this point we have different area. And as we move to the top, the area is also changing. So if area is not constant, the maximum force which this bone can bear will also change. That's why there's a difference between the calculated value and the true account value which is given in the book. So how the structure shown in the diagram would account for difference from calculated value. So what is the reason why the calculated values are different? The effective area for the cortical bone is not same as what we use in the previous calculation. So effective area is less. So if effective area decrease, the force which it can bear will also decrease when the stress remain constant. Is it clear, this question? Next is 22. A thin wire of a uniform cross-sectional area is stretched by increasing the force. The corresponding stress strain graph is there. Select the row which correctly describe and identify the yield point, the limit of proportionality, and the elastic limit. So how we can work out the position? The limit of proportionality means the last point where the line is straight. We call that as a limit of proportionality. And yield point means for a small change in force, there is a maximum change in extension or strain. We call that as yield point. So if we work out the proportionality limit first, proportionality limit is the last point where the line is straight. So it appears that till W the line is straight. So it means the proportionality limit is W. So either A will be answer or B. Then yield point means when the region, that because yield point region is the region where this graph is parallel to the strain axis or extension axis. So this is a yield point region, or the point within this region is known as the yield point. So what will be the yield point? So yield point will be Z. And what about the elastic limit? Because the yield point, we have two options. Either Y can be a yield point. There are two possibilities. Either Y can be a yield point or Z can be a yield point. But what will be the yield point? Yield point is a region where this is parallel to strain axis or extension axis. So, or very small change in force, there is a maximum change in extension. So that refers to Z. So yield point is Z and limit of proportionality is W. So in between them, there will be elastic limit. That's why B is the right answer for question 22. So question 22, then we have 23. In question 23, a force is applied across the end of a spring. The following force and extension graphs are there. 3 points P, Q, and R are marked. So if we don't apply any force, the object, when no force is applied, so the spring will be at its original length. Here, basically a positive force causing an extension, like extension means increase in length. So it means R should be a point where the length should increase. So when we are increasing the length, means we are increasing the force, the length should increase. And then P what happened? Because force is in negative axis means the direction of the force is opposite. So it means at P we are compressing it. So when we are compressing it, the size should decrease. So at P the size should decrease, at Q it should be original length, and at R the size should increase. That's why A should be the right answer for this. Is it clear? So in question 24, silk is a natural protein fiber produced by spider and silkworm. It is a material of high tensile strength, means maximum greater amount of force is needed to tear or break that. The graph gives a stress and strain curve up to a point. The silk produced by a spider and by silkworm. So this dotted line is by the silk of silkworm, and another one is the silk produced by the spider. State what is meant by high tensile strength. So what is the definition or meaning of high tensile strength? It means maximum force or greater amount of force is needed to break the object, to tear the object. We call that as high tensile strength. And or greater amount of force is needed you can also write the definition: high tensile force on unit area. A greater amount of force is needed to stretch the object and break. Because the term tensile refers to when we stretch. If it was a high compressive strength, it means we need a greater amount of force to compress the object until it shatter or it break. The next part is the spider use silk to build a web to catch insects. Use the graph, explain how the protein of a spider silk made it more suitable than a silkworm for building a web to catch insects. Because silkworm is not using the web to catch the insect, but spider is using its web to catch the insect. So from this graph, how we can conclude, or what we can say from this graph, that the spider web is more useful for catching the insect rather than the silkworm. So number one, you will compare the characteristic of the graph. Number one, you will compare the slope. You can see the spider web, the sketch for stress and strain for spider is more than the steep, like the slope, the initial slope for a spider web is more than for a silkworm. So what it shows, it means that this spider is having a high young modulus, and silkworm is its web is having a low Young's modulus. That is one thing. Then the second, you can clearly see for a spider there is a high tensile strength. Means very like greater amount of forces needed or greater stress is there at which it break. But for a silkworm, the web can break at a lower. It's about approximately half of it. So second thing, when you can compare with the tensile strength, because when the insect trap in a web, so what will happen? The insect will also apply a force to come out from the web. So as a result, when insect will also apply a force in case if the web is made from a silkworm or by the silkworm, the insect can easily break that or tear that web as compared to that of spider. So it will have a high tensile strength, a greater tensile strength is there. Then you can also compare area under the graph. Area under the graph shows how much energy it can store before it break. Like it is also area under the graph refers to toughness. So you can see the spider web is having a greater area under the graph. So if it is having a greater area under the graph, it means it is also tough. Means it can absorb greater amount of energy before it tear or break. Is it clear? The comparison between the web of spider and the silkworm. So these are the parameters which you will always compare. Then use the graph, determine the Young's modulus. How to determine the Young's modulus? So to determine the Young's modulus, it is stress divided by strain. And we always take use a graph to determine for spider. So we always take only the straight line region. We don't bother about what happened afterwards, only the straight line. So Young's modulus is stress divided by strain. So we'll take a value of stress and divided by strain, we will get the Young's modulus. Or we can work out the gradient y2 minus y1 over x2 minus x1. We'll get the Young's modulus. Then insect flies into a spider web and become attached to a single thread, which create a tension of 580 micronewton. The thread extended approximately 3% of its original. We have to calculate a radius. So first, as we know, we already calculated the Young's modulus in the previous part. So we know Young's modulus denoted by E, we can denote by Y. Young's modulus is stress by strain. So Young's modulus, stress is force divided by area and strain is change in length over original length. So if I simplify the formula, stress is force by area and strain is change in length over original length. So when we simplify, it will be FL divided by delta L A. So the force we have, which is 580 micronewton. So we have the force. Dimension, the thread extended approximately 3% of the original length. So means the change in length is 3% of the original length, or we can say 0.03 of the original length. So in place of delta L, we can write 0.0 L. And Young's modulus we already calculated. So Young's modulus is there, F is there, L, delta L is 0.03 L, and area. So we have F, L will cancel with L, and we'll work out A. After getting the area of cross section is pi r square or pi d square by 4. So after getting the area divided by pi and take a root, we'll get the radius of the thread. Is it clear, this question, that how we work out the radius of the thread? Next is question 25, B2. 25. State assumption. The assumption is in one is incorrect. Explain how this affect the calculated value. Basically, what we assume here, we assume that the area, like there's a foam cube which is 7 centimeter side is compressed. So we assume that the area won't change. That is our assumption. But practically, when you compress a foam, then the area will also change. And as the area change, the maximum force, or as we calculated the Young's modulus is stress divided by strain. So If we are applying a constant force, like stress is force divided by area, and area is not area is continuously changing here, this is 20. Okay, there are two. 24 is there. Okay, the first one is after that, 25. So basically what happened, the area is not constant. When we compress something, the area is, because it start to, when we compress something, the area is not constant, areas start to increase. And we have the formula that the Young's modulus is stress divided by strain. And stress will change. How the stress will change? Force is constant. Area is increasing. If area increases, the stress will decrease. And as the stress decreases, the Young's modulus will also decrease. So it won't be accurate.